Hi guys, this is further to our earlier video of primary current injection where we explained you how does primary current injection works and mainly the uses of it. Okay, now this video is the extension of MCCB tripping demonstration where we all know that MCB has got two tripping characteristics. One is due to thermal and the another one is due to magnetic. The tripping is mainly depends on two components. One which is the magnitude of the fault current, and the second is the time to trip. Okay, in MCB we have got four types: type A, type B, type C, and type D. And the magnetic tripping varies with these types. So for let's say type C, the magnetic tripping occurs between 5 to 10 times of the I nominal, that is nominal current of the MCCB. Okay. And for tripping, it takes normally between 10 to 20 milliseconds. Now the purpose of this video, as I said, the extension of the earlier video. Now here what we are trying to show you or demonstrate you is the tripping time variation with respect to the magnitude of the fault current. So here we have now we'll show you how we are going to do it, and we'll show you the graphs as well. Okay, so let's go for the demo. For injecting fault current, we have used our own manufactured current injecting source. We have used inductor as a load and 10 ampere C-type MCB as a tripping device. To measure the fault current and time, we have used high-end power analyzer which can capture waveforms. Here to get the rated current flow, we have made some circuit arrangement. As you can see, the tripping MCB, then inductor in series, and then we are going to create the ISC, that is short circuit fault current, and then we will observe the MCB tripping. Now let's see how it is made. This is showing the current injecting source arrangement. These are the cable connecting probes connected to the inductor as a load. Then this inductor is in series with tripping device, that is C-type MCB, which is 10 amperes IN. So this is the complete arrangement. Now this is the power analyzer which will capture the tripping. And now this is showing the waveforms presently. Now we start with demonstration. Now we are making MCB, it is actually an on condition. Okay. Now see, the load is increased. Now it is almost 10 ampere, you can see here. Now we are going to stabilize it to some variable currents. Now we are shorting it, so now the MCB got tripped. Now this is the power analyzer image which has been captured during fault conditions. So the first cycle, you can see this is the normal load conditions, and the second cycle is the fault conditions, where in the second cycle the MCB got tripped. Now to get a higher values of current, we are now putting two inductors in a series. So this is the circuit diagram for the same. So the two inductors in series, so it will increase the voltage drop, and here on it can increase the ISC, that is fault current. So we can see how does the MCB behave in higher amplitude of fault current. Now again I am showing you the connections. Now the two inductors are in series, so the voltage drop will be higher and the fault current will be also higher when we will be shorting it. Okay, at the arrangement, MCB is now in trip condition, it is not on. We're making it on now. MCB is on, right? Now if we will be now increasing the load, now the load is increasing, we will stabilize it to somewhere around 8 to 9 amperes. Okay, so 8.0204. Okay, we have stabilized it, and now taking time to stabilize it. We'll be shorting it. Okay, now see the shorting and MCB trips. MCB trips. So MCB got tripped, and this is the another waveform that we have captured in this situation. Now you can see the peak values has gone to 235 ampere, and you can see the tripping cycle is narrowed. It is not a complete.
Now we have carried out the test for various loads and various fault current to understand the relation between magnitude and time. Then we will now show you two such a conditions for understanding magnitude of fault current versus time. Now let's analyze the waveform of our analyzer meter, which actually gives you the data points for every 78 microseconds and captures 4 cycle in a window. So this is a window wherein it can capture a 4 cycle, and each cycle is comprising of 78 microseconds data point. Now let's see the first situation. This is the situation, or this is the region wherein the load was normal, and this is a point at, you can say, 0.020 seconds, that's 20 millisecond, the fault started, and this is a time when the MCB got tripped and load suddenly drops to 0. Now we'll analyze what is the time taken for the tripping and what is the magnitude of fault current. So now we analyze and we calculate it. So this part was having a load of 8 ampere, and this part, after calculating, we got this part to be 69 amperes. Now as you see, the fault started at time 0.02 seconds, and if you can see here, it got tripped. So this is 0.41 seconds. So if you take the difference, this is approximately 21 millisecond. So fault withstood to for 20 milliseconds. The fault was 69 amperes. Now we'll have another situation where we increase the fault. Again here the first region was having a normal current of 8 amperes. Now you can see this is the time where the fault started. So you can say the time, I'll show you, 21 millisecond the fault started, and this is the time when fault vanished. So 21 second it started and it got 0 to 0 at 0.24 second. So you can calculate this fault withstood for 3 milliseconds, and the fault magnitude, if we calculate, it goes to 174 ampere. And if you can see here, the scale shows you 250. So the calculation is not at 250 exactly, but it was at 174 RMS value here, and the tripping time, you can see, just 3 millisecond. Now with this, I think we have completed what is the purpose of the this complete video, and I think hope this will help you, and you will like this video. With this entire exercise can give us an idea and testing result for confirming time current characteristics of MCB. We aim to put more such a theory and practical videos to help all of us understand electricity in a better way. We wish to we wish viewer inputs and your problems so we can work on the same and put the solutions on the videos. To see more videos on this, visit our website at it's www.electricalequipmentdesign.com and www.electricalsciencesolutions.com. Thank you very much.